So, welcome back again. I hope that you are enjoying the lectures again and getting some idea about fundamentals, about the aerosols, about air pollutions, different techniques and their impacts as well actually. One of the important kind of properties that aerosols have, because when the aerosols since the aerosols are suspended in the atmosphere and these aerosol species must be interacting with the incoming solar radiation. So, because the aerosols are interacting, there will be a changes in their properties. So, how these properties, they are optically active with the solar electromagnetic radiation. So, when we say that how they are going to change, for example, scattering, absorption or extinction, and how they are important for studying the air pollutions and then some of the physics behind this one. So, in this lectures we are going to discuss about the aerosol optical properties. I think it will be continued lecture for another 3 to 4 lectures on aerosol optical properties, because we need to complete this section at least 3 lectures or so, 3 or 4 lectures. So, let us begin. So, when we talk about the aerosol optical properties, these are the listed aerosol optical properties that we usually talk about. We usually talk about AOD, which is aerosol optical depth, and this is kind of and then the another one is called aerosol index. And aerosol optical depth and aerosol index, these two are actually used to understand the abundance of the aerosols in the atmosphere, or how the atmosphere is, whether it is highly polluted or less polluted. So, the pollution levels can be actually kindly note that here the aerosol optical depth, it does not discuss about the scattering or absorption due to a gaseous molecule. It is only talk about the aerosols due to the aerosols, and these aerosols we will see and there is a difference between aerosol index and optical depth. So, we will come to that equations later, and this aerosol optical depth, when we see these aerosols, for example, can either absorb the radiation or they can scatter the radiations. We will come in the next slide again, but just remember these are the two very important processes, and when we combine these two, we usually called them extinction. So, this is usually written by B extinction. There are different notations for this one, so don't be confused with this one. My sincere advice would be that you refer whatever the books, but you make your nomenclature so that you are not confused, because in the aerosol optical properties there will be terms like mass absorption efficiency, mass scattering efficiency, and then extinction efficiency, something like that, and then you will have absorption, scattering and extinction coefficients, and some of the these terms are very confusing. So, just make sure that you are using your own nomenclature. Then with these two parameters, we also calculate one of the very important parameter, that is called single scattering albedo. It is like we talk about the albedo because of the particular surface, that how much radiation is reflected back to the atmosphere when compared to the incoming solar radiation. So, this we will discuss here. That is not reflected when we talk about here single scattering albedo is because of the scattering, not because of the reflection, because particles, we are talking about the particles here. So, particles will not reflect much, they will scatter more the solar radiation. Then as I talk, there will be terms like mass absorption efficiency, mass absorption cross sections. These two are same, but they are actually very confusing. So, just another advice would be that you remember them with their units, actually what units they have. So, if you remember the units, you can do this one. Then MSE is actually usually mass scattering efficiency, we will come to that. Then another very important factor is asymmetric factor. Then these all the parameters, they are used to calculate aerosol radiative forcing. Here I mean direct aerosol radiative forcing only, and we will discuss these things in the coming slides. We will also have some suitable examples, typical values and the range. So, this is you see very important and good slides. Okay. So, here you see this is absorption by the surface. Okay. When it is whatever the surface is there, what is the amount of radiation that is actually absorbed by the surface, and then you can have scattering and reflection by the surface. So, these are the three processes that is related to the surface properties, but when there is a emission, you produce lots of aerosols, and these aerosols are very tiny particles, as we discussed, in a few hundreds of nanometers to 10 micrometer or so. And then what they do, they also have a similar kind of absorption and scattering effects. So, they either absorb the radiation or they scatter the radiation. Okay. Just in a corollary, you can also see here the gaseous molecules. Here we are talking about the gaseous. So, it is mostly we are talking about the gaseous molecules that are there in the atmosphere. So, these gases can also absorb the radiation and scattering, and we will discuss that how this absorption and scattering between the gas and then particles are different. So, this will be there, we will discuss that one. Another very important component of the earth system is actually clouds, and clouds do scatter and reflect the solar radiation. There could be a cloud scattering within the cloud itself, and then the clouds, there could be a part of the radiation can be transmitted through the clouds. So, these are the things that if it is depending on the thickness of the clouds, if cloud is not very thick, then it can be actually transmission can be there. So, now in principle what we are having four systems here: absorption and scattering by the surface, okay, one component, then scattering and absorption by the aerosols, scattering and absorption by the clouds, and then scattering and absorption by the gaseous molecules. We will mostly discuss about the gaseous molecules and aerosols, but just remember that we will not again discuss too much on the gaseous species. We will have more of aerosols, because this is a kind of anthropogenic one, and that is causing lots of disturbances in the atmosphere. Okay. This is what happens when the radiation interacts with the particles. So, here the radiations means, when I say it is electromagnetic radiation or solar radiation. Okay. Okay. You have an incident light, and here for the complexity, let us assume that the wavelength is lambda 0. So, the constant wavelength, and we are talking about here. So, this means we are talking about the monochromatic light that is there. We are not talking about the all the wavelengths here. We are discussing only one wavelength, for example. So, just to understand the things, and this is the typical say particles, atmospheric particles that is there. Now, what will happen? One of the things will be there, that when the particles radiate can interact with this one, it can either absorb the radiation, and if it is absorbing the radiation, what it has to do? It can do thermal emissions, for example, black carbon. So, when the black carbon absorbs the radiation, it heats up black, because the energy is actually is now that the energy that was there in the atmosphere, solar radiation, that energy will be absorbed by the black carbon molecule or black carbon particles. These black carbon particles will have high energy now. They will contain some more energy. So, this energy has to be because when the surroundings become cooler, they re-emit the radiation in the thermal emission form, and then they actually the point to remember here is that they will emit not only lambda 0, they will emit all kind of radiations here, and then part of the radiation can be reflected back. And remember, in absorption and thermal emission, the wavelength is going to change, but when the reflection is there, the wavelength of the radiation is not changing. So, the same wavelength is reflected back. Then you can have a Raman scattering. Here also the wavelength of the light will change. You have fluorescence, it can have fluorescence particles emit the radiation, then in that case also the wavelength will change. Some of the particles can be just deviated from their path, and they are not at all interacting with the particles, they are just away or on the surface, just little bit away from the surface. So, they are not interacting at all, they will just be reflected, because of, like, in the winds, when the winds is there and you have something object. So, the winds will be like, from the winds, when this is going little bit away, it will be just deflecting like that. So, that you have actually. Okay. Then there is another important process, that these particles can also do diffraction, and in the diffraction this wavelength will remain the same. Okay. Another thing is there, that when this particle is falling on here and its part of radiation is absorbed, and its part, if it is actually, if transmission, it can actually go through, and if it changes the path after passing in the particle, then it is called refraction. So, here also the wavelength of the light will not change. So, for the complexity there are so many processes, and these are the processes in principle. And if you remember my discussion on the instrumentation, that these are the different properties or physical properties that can be used to measure some of these properties, aerosol optical properties as well as the chemical properties. Okay. So, just remember these, there are so many processes, but in coming aerosol optical properties, we mostly talk about the absorption, scattering, and then extinction. These are the three things that we are too much interested, or we will be highly interested. So, let us go see and see what are the things that are there. Okay. When the aerosol light scattering is there, so for example, you have a sun, it is emitting say 100% total solar radiation you have, and this is the top of the atmosphere. Okay. And Earth's atmosphere, so about 30% of the radiation will be reflected by the clouds, atmosphere and the earth. Okay. So, on the earth surface about 30% is actually reflected by. About 19% of the solar radiation, okay, out of 100, 19% of the solar radiation will be absorbed by the clouds and the atmosphere. So, now you see here, reflected by the clouds and atmosphere is about 30%, 19% will be absorbed by the clouds and the atmosphere, within the atmosphere, and this is actually this is example, and this is where it is if this absorption is higher, if this absorption increase, then what will be happening? You will be having a temperature increase in this one by whatever processes, whether it is because of the carbon dioxide increase or the aerosol concentration increase. So, this can happen, and then so this means you have now how much, 30 and 19, you have 49% that is either reflected by the clouds or the atmosphere, or it is absorbed by the clouds and the atmosphere. So, 49% is there in the atmosphere and above the atmosphere. The remaining 51%, this actually is absorbed by the land and water, and this is very important. When these land and waters that is there, they absorb the radiation, and when the surrounding becomes cooler, so they will re-emit actually. So, this balance is very important. If you just see this earth's balance, this is very simple, I have explained. Now, you can further do calculation for the aerosols and gaseous here, but that will be too much for discussion. And what I am going to do here, there are different types of one phenomena that I told, that it is scattering. So, the phenomena of light being deflected in multiple directions. So, for example, this sun is radiation is coming, sun radiation will be coming from all the direction, all the 4 directions. So, similarly, when it interacts with the particles, the radiation will be deflected in multiple directions, and sometimes you will have a forward scattering and backward scattering. Okay. And for example, light can scatter when hit by a very small particles and is deflected in all the directions. So, there will be 2 examples, one will be actually forward scattering, when waves are deflected by the small angles, okay, and continue to move in the similar direction as before. They will be deflected, but their deflection is very small and they will be moving in the same direction. So this kind of scattering is called forward scattering, and this can happen with many types of waves including light, X-rays and water waves. But of course, we are discussing here about the electromagnetic radiation, that is also sort of light or waves. And then apart from this one, there will be a Rayleigh scattering, when light or the other electromagnetic radiation is scattered by the particles that are much smaller than the wavelength of the radiation. So, the diameter of the particles is much smaller than the wavelength. Okay. So, the incoming wavelength. So, this case, this will be a Rayleigh scattering, and this is what when causes the blue sky and the sky during the day and night time, reddening at the sun rays. So this is actually caused by the particles, smaller particles whose size is much smaller compared to the incoming solar radiation, wavelength of the incoming solar radiation. And then scattering cross section is defined as the area that a target blocks during the scattering event. So that how much actually the area will be there. For example, if it is a sphere, the scattering cross section will be pi r square. So, as we discussed, scattering occurs, sorry for the typo, scattering occurs when particles or large gaseous molecules are present in the atmosphere. So, scattering can happen because of the particles as because of the gases, and due to the interaction, electromagnetic radiation is redirected. This is very important. There will be alpha, the angle of deflection is small, okay, and they move in the same direction. Okay. The path will not change. So, the next question that comes, that how much radiation can be scattered, how much scattering can be there, and this depends on the many of the important factors. So, for example, there are few are listed here, that wavelength of the radiation, abundance of the particle or gases, how much their concentration is there, the distance the radiation travels through the atmosphere, and this is precisely the example when the sun is usually in the top noon time, the radiation is directly coming, the path length is come, and when in the morning and evening time the sun is horizontal or kind of it has to cover larger distance. That time what will happen? It will, because it has to travel larger distance, and it has to, then means it will encounter more scattering, and when you have more scattering, this the wavelength, of course you can see the redness during the other times. So this is just corollary to what happened with the particles when you consider nucleus, like because the nucleus, and when some light particles are attracting alpha particles, for example. So here the alpha particle is also like positive. So how it will going there? I am just giving the corollary. So don't just completely correlate with this one, because it is a positive molecule. In other sense, in electromagnetic interaction with the electromagnetic radiation with particles, there is no positive or negative charge. So here you have positive charge, this will be actually reflected back, and this can be, the angle is called scattering angle, and then you can talk about this one. Okay. Similarly, what happened when a beam of alpha particle passes through? So there could be a small deflection, or most of the alpha particles pass straight light, they do not encounter this one actually nucleus, they are little bit away from the nucleus, and when they are very close, there will be actually large deflection can be there, and then most if it is actually directly hitting the nucleus, then they can be turned back, and then could be a backward scattering kind of things. And so this is atoms of the gold foil, that is how it is actually seen, and how the alpha particles interact with this one. So just I have given a corollary, so you can just relate this one. One thing that is very important, that we calculate what happens because of the aerosol light scattering and absorption, visibility will be affected. And what is the visibility? Is the farthest distance that one can see and identify an object in the atmosphere. So this means what will happen? So when that atmosphere is closed and the atmosphere is clear, Okay. Our radiation from the eyes, they can go and see larger distance. You can see the object, you can identify the object that is even very large distance. But when you have lots of pollutants, what will happen? This radiation is going to be either scattered or absorbed by the particles, and because of that one the visibility will reduce. So, visibility is inversely proportional to kind of extinction, and if I just remember, I defined B extinction like B extinction. So, if you just calculate, visibility is inversely proportional, and we will calculate some of the parameters from here. So, absorption, this one I just give in the previous lecture, we will discuss absorption more later. Scattering, when the Rayleigh scattering is because of the particles when the diameter is much less than the diameter the wavelength of the incoming solar radiation, and it's usually when that is more particular when diameter is about 0.3 micrometer. Okay, and maximum of the scattering, Rayleigh scattering, happens because of the particles of 290 to 750 nanometers. So, these are actually very now you can remember, these are actually scattering because of the fine particles, because we defined. So, this is actually like these particles are nothing but they will be PM1, okay, not PM2.5 and PM10. So, we will see that how they are there, and when there is a particle, when the diameter is actually similar to the order of the wavelength that is coming, then you can have this one, and this becomes more prone when the diameter is less than 10 micrometer. You can just remove 0.3 here, you can just put 0.75, okay, micrometer, because why I am telling, because 0.3 less than 0.3 anyway you are going to have a Rayleigh scattering. So, 0.75 to kind of less than 10. So, here actually like particulate matter you have, say if I just say PM 0.75, so 0.75 to PM10, these particles, and here you will have, this means in between you have PM1, you have PM2.5, and you can have PM10 particles. So, the scattering, my scattering is because of the particles, larger particles. Okay, just remember these differences. Rayleigh scattering is because of the smaller particles, smaller size particles, and my scattering is because of the larger particles. And extinction coefficient, as I discussed, is the sum of the scattering and absorption coefficients. So, this actually I talked about Rayleigh scattering and my scattering. There can be another scattering is non-selective scattering, and I think, okay, just let me brush through this one. Rayleigh scattering is mostly when the particle size is actually much smaller than the lambda, and this is the precisely case for the molecules, okay, and this is actually for the gaseous molecule. So, if somebody asks you that Rayleigh scattering happens because of the smaller particles and gaseous molecules, this is not because of the bigger particles or aerosols. So, maximum of the Rayleigh scattering is because of the gaseous molecules, and is the dominant scattering mechanism in the upper atmosphere, okay, because that is where you have the abundant kind of things. Then sky appears blue in the color due to this kind of scattering. So, the blue comes because of the Rayleigh scattering, and that is why. Okay, and then you have my scattering when the particles are just about the similar size, so diameter is about the wavelength, then it will be there actually. Dust, it could be because of the dust, pollens, this is pollen, smoke, water vapor, that are common cause of my scattering, which tend to affect longer wavelength than the Rayleigh scattering. This type of scattering occurs mostly in the lower portion of the atmosphere, and since we are talking about the air pollution is mostly in the where this is actually lower atmosphere. So, this means my scattering will be very prominent here. So, this is where, so my scattering, if somebody asks you my scattering is where, is more in the lower atmosphere. Non-selective, the final scattering is non-selective scattering occur due to particles that are much larger than the wavelength of radiation. So, here the diameter of the particles is much larger than the lambda, and this is for example because of the water droplets and large dust particles that can cause this kind of wavelength. So usually this we say that lambda is more than 10 micrometer, okay, because when we say consider the wavelength that is coming, it's coming from all the way from gamma solar radiation to X-ray, then visible ultraviolet, visible IR, and then you have Hertzian wave, microwave, okay, these are the things. And then when so this is more than 10 micrometer particles, you have non-selective scattering. And this name comes because there is no selective. So all the particles and all the wavelength, they will be scattered about equally, not much actually, okay. And this type of scattering causes the fog and clouds to appear in our eyes, because blue, green and red lights are scattered in approximately equal quantities. Sorry, again typo. So so blue plus green plus red light is actually like white light. So and when this is dominant because of the particles that are larger particles, and when there is a kind of fog and clouds, then we have a bigger particle. So this non-selective scattering will be common. So with this one, I think I will stop here about the scattering, and in the next lecture what we are going to discuss about the some of the equations that we will use for the calculation of these parameters, and for example the extinction and absorption coefficient, and then for example aerosol optical depth we will be discussing in the next lecture. So thank you.